time. And today's speaker is Mykola Vovchanskyi with the talk on inverse dual flows survey and some results. Please. We cannot hear you. No. No, we cannot hear you.
Может выйти и зайти по новой?
Yes, I think that it will be better to restart. Okay.
Так, а сейчас?
Okay, and now we can hear you.
I don't know why this happens regular. I just don't know. It's Linux, so maybe something with Zoom. So let me reshare the screen. So everything was okay.
Okay.
So I will be talking about one very specific topic about some construction of so-called dual flows. About two specific papers, about some my results, and I will end with a quick explanation why my interest was renewed in those. So let us start with some examples of flows. Then we very quickly talk about what duality is. And we have some case studies, and then we will proceed to my results. So, I will name some sources right now, and then I will add something during the talk. So this is the first paper is a general survey. I'm not going to discuss it, but it treats different types of duality for Markov process very in great detail. I will be talking about these two papers. This particular is a continuation of work of Akahori and Watanabe. And this particular paper is a continuation of work of Norris and Turner. And about these two papers by myself. So let's start with a few classical examples of stochastic flows. So first, let us consider what can be called Kunita-type flows or homomorphic CK, that is smooth, sufficiently smooth flows. We have a standard stochastic differential equation which admits a unique strong solution. And we can speak about a family transformation of the real line, which is defined by this specific transformation mapping. To describe such flows, a pair of so-called local characteristics is used, which is drift. I will always use B to denote drift. And the second one is effectively joint covariance of the corresponding components of white noise. Another classical example, which has been discussed extensively on this seminar is Brownian web. So coalescing Brownian motions move independently until they meet. Now, strictly speaking, to define a flow in this case, contrary to the case of smooth flows, some additional work is required. And I will not care and I will not discuss any fine properties that are related to flow as a dynamical, strong dynamical system, as a proper cocycle. And I will refer to talks by Dr. Ryabo and papers by him and his co-authors. Now I will also discuss coalescing Harris flows. So again, this is different from the previous situation in the way that every single particle behaves as a diffusion with constant diffusion coefficient, unit diffusion, and some drift. And this Wiener process depends on the starting point. It also depends on time s. And they are correlated in this specific way. Phi is called infinitesimal covariance. To define such a flow, typically imaginary problems are used. And if you want a purely coalescing Harris flow in the way that we can even discuss what a flow is, because generally speaking, one can propose examples on B and phi such that it's not known whether this is a coalescing flow, whether it has discrete values, locally finite set of points at every time, or something else happens. So we need to impose some condition on B and phi. This condition has been presented already, so I will just quickly repeat them. So we need phi, a classical assumptions on phi, continuous symmetric, strictly positive diffusion outside of zero, Lipschitz continuous outside of neighborhood. 1 at 0, so it doesn't really matter, and drift B should be regular in the terms of some external function non-negative, such that has this estimate with possibly negative beta, so it can be actually unbounded. And if we compare this with a standard regular assumption on phi, then we can discuss a proper coalescing, purely coalescing Harris flow in this very case. This is what I mean by a Harris flow. Now, this example is taken from a paper by the Japanese authors previously mentioned. So let us consider a flow of a good stochastic differential equation with very good coefficients, such that no singularity ever happens. We even can assume that sigma is bounded strictly from 0 on the whole plane. So 0 is just a 0 point if we consider one particle motion as a diffusion. And we allow it to live in the upper half plane as just stop when it hits 0. So this is a flow of stochastic differential equation with absorption at 0, forced absorption. The dual flow for this flow is actually well defined, as we will see. So we will discuss only autonomous case. We will not discuss any extension for unbound coefficients, even if they are presented in the corresponding papers. And again, in this case, one can look for classical paper of Kunitev for the existence of a very well-behaved version of the flow in all variables, S, T, and X. And in these cases, we need to be careful about taking right or left continuous modification of the flow if needed. And let's just assume that we always take right continuous version. Now let's recall what a flow is. So we need a set of non-decreasing Cadillac functions and a family of random elements with values in this specific set. It's called a stochastic flow if it satisfies a weak cocycle property. has independent increments, has stationary increments, and stochastic continuity in the sense that it converges to identity, x as t converges to identity when t goes to s. Now, in which sense convergence happens? So which topology is defined on D? More or less consensus is that some version of a Levy-Prokhorov distance for probability measures is used. Typically, we just use it locally and then consider essentially local convergence on compact sets in this step. I, for some reasons, used always J1 topology on D, and there were other approaches. For instance, Norris and Ternan were suggested to consider simultaneously not just right continuous version of the flow, but also left continuous as a pair. But then again, using this Levy distance, because it's essentially defined in terms of graph of a function, one can use the same formula for this pair and even do proper corrections in the way that taking inverse function then is going to be in geometry in a properly defined distance. So different choices may lead to slightly different technical calculations. So one example is if you consider a purely coalescing flow being approximated by homomorphic flows, so say after some modification procedure applied to coefficients, then Levy-type convergence should be a normal choice. But if you try to do this in J1 topologies, this is not going to happen because the prelimit flows are continuous and the limit flow is discontinuous, so it cannot have good convergence. And a proper way to discuss it is to go for weak star convergence in the dual of this space of functions vanishing at infinity of push-forward measures. But essentially, this is pretty much the same. This is just a different way to talk about things. So what is a dual flow? We will define a dual flow by this formula for every pair, fixed pair S and T, where this is either a real inverse or a generalized inverse, either right continuous or left continuous version. Again, let us assume that we always take Katlak version, but typically the difference is minimal. Effectively, I have to say that since these formulas are very easy to read and very easy to operate with, people tend to do a lot of mistakes with them. But generally speaking, even if something is written with the wrong version of generalized inverse, you can repair the proof. And a very natural, purely deterministic result would be as follows. If we consider our flow for S, U, and T, and we know that this is a coalescing flow of some type, to be able to have this cocycle property, group property, we need a special relation between the points of discontinuity and the set of points where this happens. So essentially that means that these points x, u, t, this is where the flow is discontinuous, they do not happen where the discontinuity for this part happens. But since purely coalescing flow typically doesn't allow to hit this precise point almost surely for fixed S and T, so as soon as we cover the whole plane, we can define a generalized inverse.
Okay, before you go to exams, as I see, let me ask you the following. In the beginning, you mentioned the work where the author introduced the general notion of duality for Markov processes. Yes?
They didn't introduce, they review it.
Okay, very good. Because I also have an opinion that the notion of duality is much more older than this.
Yes, obviously.
Okay. But let me ask you the following. You define the dual flow analytically, like infimum of soup of something. So let me ask you, do we get the dual Markov process in a sense of
Yes.
duality of Markov processes?
Yes, and we will exactly discuss two papers where it's proved in different settings by different methods.
Okay, good.
Because obviously this needs to be proven, because without understanding what is this is just an object. There's no
Yeah,
real value.
surely, surely. Okay, good.
So if we speak about good flows, and we will see how they are constructed, we have CK mappings, a flow of CK mappings, and we can take just inverse mappings in a proper sense. And it's done extensively in the book of Kunit. And he has the following results. That if we have a flow with local characteristic B as a drift and A as a joint covariance, then its dual flow is again a flow with the same joint covariance and a corrected drift. This correction is actually exactly the correction when moving from the Ito calculus to Stratonovich calculus, as we will see. And we will revisit this observation. Now, if we speak about Brownian web, by using, say, approximation of a Brownian web by coalescing random walks, it's very easy to understand that the dual of a Brownian web is the Brownian web itself. Now, when drift appears, we have the change of the sign before the drift. It was first strictly formulated by Dr. Rebel. Alternatively, which also works in the case of Harris flow, you can do some good approximations. There is papers by Dr. Drogovts on this topic, and you can actually use this approximation and see that this happens. Now, there is no correction to this drift because what happens to be a covariance function is symmetrical. So when you approximate it by good modifiers, it stays symmetrical, so this just disappears. Now, coalescing Harris flow, they share the same pretty much picture. If there is no drift, we obtain the same flow. If there is drift, you need to change the sign of the drift. Obviously, you cannot just use random walks, so only this second method works. Let's move to the example with the flow with absorption at 0. And it was noticed by Levy in the 40s that the dual flow for the flow with absorption is a flow with reflection at 0. So this is the flow where one point motion is described as a solution of the Skorokhod problem, where this is a function that decreases only when this hits 0, and this is related to local time, etc. And when it's away from 0, it effectively just a solution of the corresponding Brownian stochastic differential equation with drift, with the corrected drift. So here the correction is written minus b plus sigma prime. In terms of Kunita, this is sigma squared because this is a for Kunita. So this is exactly the same. This. Now, before moving further, let us very quickly recall just a general definition of what duality is typically, what is understood as duality. So if you have two Markov processes with proper semigroups, the duality with respect to function f, with respect to a function from certain class, is to have this relation. Or in terms of semigroups, this. In particular, if you take this function f to be equal indicator, you recover a very natural and something that you would expect from our construction of a dual flow as a generalized inverse. So effectively, the probability that the original flow hits above y is the probability that the dual flow moves along this trajectory and hits less than x. So effectively, we have this picture, which is exactly what happens for Brownian web. We know the trajectories of a direct and reverse Brownian web do not intersect. Now, from this, duality in terms of generators can be read, but again, there is a lot of stuff happening, including analytic stuff and discrete schemes, etc., etc. What we are discussing, we are essentially discussing duality via sample paths. So in particular, as soon as we do not have problematic measures, if you have just absolutely continuous distributions of our it means that this x of t can be seen as a measure with no atoms. We get this by construction in our scheme. So it can be read that
excuse me, can I ask you, you say law x is t. Did you mean that x is t with respect to special variable is Kadlak function, so it can be considered as some in brackets distribution function of some measure? Am I right?
Yes, yes, yes.
Okay,
yes.
but it can be continuous, but this measure can be similar
Yes.
to the back measure, yes?
Yes, it's strange. This is not needed. I think I made some mistake.
Mm-hmm.
Yeah, because it doesn't make sense. If you look at the constructions and you get this more or less for free, this part. Because the generalized inverse will work like this.
Yes, surely.
Yeah.
Mm-hmm.
And
So
we'll actually...
you don't need those
Yes,
something like those statements.
yeah, it's in written strangely. It's something.
Mm-hmm. Okay.
So let's look at two explicit proofs that establish what a dual flow in two particular oscillation is. We will look at paper of Bell and a paper of the Japanese authors. And Harris' flow will be revisited later. So let's start with flow with absorbing reflected boundaries at zero. So I will briefly sketch the proof so we can understand how it happens. So if the dual flow is positive, then this family around this point where it stays positive is going to behave like a SDE with a corrected drift as an application of the following classical result that can be found in the book of Kuniti, Kedawatanabe, etc. And it goes as follows. If we have good coefficients, twice continuously differential bounded derivatives, and let's assume they are also bounded, and we consider a Stratonovich equation, and we redefine a Wiener process by inverting in time on a fixed time interval, then we can discuss another Stratonovich equation on the same probability space with this corrected inverted Wiener process and reversed drift. And this is exactly a dual flow for the original flow in this very sense. So how to obtain this result is actually very easy. And I want to say that among the participants, there might be people who attended my lectures on stochastic differential equation as their approximation, and this is exactly what we discussed. That if you, instead of the original Wiener process, take its approximation with, here is just linear approximation. This is a piecewise linear function, but you can take another types of approximation. And you try to replace in the original equation this term by this function and solve it piecewise as a still TS type ordinary differential equation, then everything is well defined, but when passing to the limit, you will not recover the original it equation. You will recover the original, the Stratonovich version of this equation. We didn't did in our course all the calculation, but we discussed this, and this is what happens. You simplify, you approximate your Wiener process. You write original flow, and original is D and the reversed is D, and passing to the limit, you will recover exactly these two objects. And one can check that for these flows, this holds automatically. So this gives us understanding how it works for good flows, smooth flows, and it also explains why this correction appears. And this is exactly the correction of the Ito-Stratonovich transition. However, this example is slightly different from the purely CK flow treated in Kunita, because we still have problems at zero. One can think that there might be, for the reflected process, might be happening some excursion. It means there are pockets where the direct flow goes to zero like this. So to discuss this, one need to apply slightly different calculations, but generally speaking, they're quite deterministical in nature with some application of probabilities. For instance, it goes in this case like this. So what happens at this point? So can we prove that the trajectory that we obtained as by taking generalized universe is continuous? And the answer is yes, because if we start from some fixed point, we cannot hit zero immediately with probability 1. And that means that the generalized pre-image of 0 is less than this fixed function. But then we can consider this difference, which is discussed in the terms of continuity. This just equals this because it's 0 by our assumption. By this, by the flow property gives this, and you effectively get this just automatically. To left continuity, this particular case proves slightly longer, but overall, it's arguments are in the spirit. Now, but this only establishes that we have a continuous function with Markov properties. But to obtain a proper characterization of this dual flow as a solution of the square root problem, we need to introduce such moments. This is a moment when we start from some previous moment and we move on the distant epsilon from it. So we start from x. We find next time when this difference equals epsilon and so on. And one can show using probabilistic methods that this goes to 0, which is a known fact for, say, just Wiener process, but here we have a SD with reflection, but it still holds. And if at the one specific such heating time, we are above the level epsilon, then the process, before it hits another heating times, is actually a solution of SD without any reflection barrier because it doesn't hit 0. And then one needs to rewrite the original dual flow as a sum of 3 terms: starting point, what is left, and what happens when this good behavior happens, where we are above some fixed level epsilon. But this difference from this very heating time tau n minus 1 epsilon to tau n epsilon is just a solution of stochastic differential equation. So it can be written in this form. Plus what is left when we replace this indicator with just this indicator. But this is going, again, can be shown to converge to 0, which means that there exists a limit to the sphere epsilon, and one can check that this phi epsilon is exactly behaves as a part of the solution of the Skrohot problem. So this example is a mixture of a coalescing case and a very good homomorphic case, because when we move outside very far from 0, nothing bad happens. We effectively have good flows, homomorphic. But here we have this pockets happening, appearing. Now let's look at another idea, which is used by Bell to provide an explicit proof for the characterization of a pure equalization flow. I have to say that when defining such flow, it's also one need to be careful. So typically it's constructed by starting a countable family of coalescent diffusion independent before they meet, which can be seen and it's sometimes called as a skeleton of a flow. And then you can recover the whole flow by taking just right limits of such diffusions and some starting points which are not covered by this countable family. So you need this countable fabric of starting points in time and space to be dense in the corresponding sense. And so we start with, I have also to say that they considered flows on circle. It's not important for our discussion. So we have coalescing flow with some characteristics, and its right or left continuous dual flow is again coalescing flow with corrected drift in the same variance. So firstly, one can see that this dual flow is Markov continuous in that sense of one-dimensional motions. And now effectively a cornerstone of the whole theory of coalescing flows reappears. So to identify the law of such a flow, we need to effectively study only two-dimensional motion. We need to describe what happens with one-dimensional motion, and we need to calculate joint covariance. This can be written in terms then of Kolmogorov characterization of diffusions, or it can be used in terms of martingale problems. But regardless of which way is chosen, we need to consider only two-dimensional motions. Here is Kolmogorov characterization used. So essentially, we need to calculate these objects and show that when divided by t minus s in t minus s, here they converge correspondingly to the drift corrected as it needed to be, and to sigma squared at x. Because this is how the theory of Kolmogorov works. And the starting point, it is exactly this relation. So the probability distribution function for the dual flow can be written in terms of the regional flow. And effectively what is done, we need to approximate the regional flow by a good Gaussian process around this x. This is actually quite lengthy calculation, so we'll only go through main steps. Firstly, we need to guarantee that we cannot get away from the starting point. And here is chosen 1/2 minus epsilon. This is actually important, and it's non-trivial. The whole estimate is standard. It's just a maximum of the effectively time change Brownian motion, but that it is possible to choose this specific value is important. And And as a result, we will exclude something with this probability. I will consider only the flow near the original starting flow. And then some linearization of coefficients happening. So for sigma is just a trivial linearization. For B is a bit more involved and strange, and I will explain in a moment why it is chosen. But generally speaking, one can expect that maybe another type of generalization linearization also works. But when you use these specific formulas, you will get a linearized approximate equation that is solvable explicitly. Now, this is quite a technical step that one can use these coefficients to define a new stochastic differential equation, estimate the error. One will need also to add to the set of excluded events something, and while we will also need to estimate this difference in terms of some time change Brownian motion, and then reapply this estimate the second time to improve it. But overall, it's doable. I will refer to the original paper for calculations, they're quite lengthy. And when it's done, you have something of this form. So this approximation is a linear stochastic differential equation with these specific coefficients, and it can be solved explicitly. There are a few cases, but if it can be solved explicitly, you know actually the distribution. Now returning to this, you will need to also expand this probability to check that indeed when you calculate these two expressions and divide it by t minus s, the proper convergence happens. This is quite lengthy calculation. Now, for joint covariance, because they're independent before they meet, it is sufficient to have this due to the Markov structure. Because it effectively means that they cannot start with a positive covariance unless they are equal. So if x1 doesn't equal x2. But it luckily can be shown by similar technique. It's just a Cauchy inequality. Instead of this, you consider a product, a square root of the product, and you proceed from there. Now, if you try to mimic this proof, in the case of Harris flow, you will need to go for this expression. But now, the two-dimensional motion doesn't have trivial joint covariance before they meet. It should be written in this form. So you will need two different Wiener processes. This is coefficients for the second one in terms of the first one. And you can actually try to repeat calculations you need, because you will need not only this, but you will need also a covariance now, properly calculated. But I never finished this attempt even in simple cases because it gets quite cumbersome very quickly. Still, I think it's totally doable. It just requires some time. But luckily, as we said, there are alternative methods to describe the distribution of a dual flow for Harris flows. But again, I'm pretty sure one can do this. Now, before moving further, let's say something about duality for the Brownian web. Here we'll recall two papers. The first is Paffin formulae for one-dimensional coalescing and annihilating systems by Treiber and Zabronsky. And the second is something that might not have been recalled on this talk. This is on the duality between coalescing Brownian motions by Xiong and Zhu. And the interesting part of this paper is that they establish a martingale problem for the measure variable problem associated with the system of coalescing Brownian motion with a fixed some fixed distribution of starting points, which is called entrance law in the terminology of Vovchanskyi. And they prove the uniqueness in a proper sense of the solution using exactly the duality. I will return to this observation a bit. And effectively, we have this nice general formula for the duality. So we have some partition of starting points into blocks, and we have some intervals, and we consider the event that all points from some block of this partition go exactly in this interval. And it can be calculated in terms of the reversed dual Brownian web, which is just coincides in distribution with the original web. So we start. Effectively, that means that if we start from some y2 and y1, the original flow before these points must go inside of this interval because they do not intersect the trajectories of dual and reverse flow, the dual and the original flow. In the Brownian web, it's also typical, especially for physicists, to consider annihilating upon meeting system of independent Brownian motion. And this is why, because effectively they like to work with such terms which are covered by the method of empty intervals. They say that our flow doesn't hit the selection of intervals, they're empty. And it can be written in terms of the reversed flow, exactly as this, and they characterize the distribution in proper sense. We will return to this later, a bit later. And I have to say that here also often alternative approach appears, which is the usage of parabolic partial differential equations for empty intervals, probabilities of moments of such flows. Now let's speak about some direct construction via skeletons. So we will consider either Brownian-Webb or purely coalescing Harris flow. And obviously, this flow can be directly reconstructed, recalling that we do not care about very fine properties and proper cocycle property from just a selection of particles that start from sk xk in this from a dance in this set subset. So, for instance, we can assume that sk is just dyadic rational, and xk just rational or whatever we want. Now let us define this set with the product J1 topology. And I will always assume that if we consider particles that start at some sk, that it is just defined before by taking its equal, by making trajectory just equal to its starting point. So this is xk, this is sk. So instead of considering a proper product of shifted in time, Skorokhod space is considered just one Skorokhod space. Now we have this generalized inverse, but it can be rewritten in this slightly more involved way. It's pretty much the same, but instead of considering just points from which we hit above x, we consider all trajectories that start before and hit above x. By PM, I will denote the projection of the first m coordinates, and QM is exactly projection of the m coordinate. I'm sorry, m minus. It's exactly projection of the m's coordinate. And now this function can be used to define this I, like exactly symbol by symbol, by rewriting it. So instead of all starting points, I only consider those starting points that are available and they're enumerated by this I, which I corresponds to SIXI, a starting point, starting position, time and space. And the rest is pretty much exactly this. And this is defined only not for all X, not for all ST, but only for those that are available in our system. This mapping is discontinuous. Let's speak about when it's continuous. It's continuous in a proper sense, for instance, in the following situation. If we have the set of our skeletons such that we know they start in proper sense, and they monotone in the sense that they cannot jump over each other, which is exactly this property. So for any pair of starting points, if we know the order, this order is preserved. And we introduce a subset of the set that satisfies two conditions. Let's start with the second one. This effectively means that for any delta, we can find such a small time interval that uniformly for this M in space, particles cannot move away from the starting position. So we take supreme over all starting points that fit in this square, in this rectangular, and we have this. The second condition means that if we start from some xk in the reverse time, so this is our qke of f of the original, and there are trajectories from the original, they hit slightly above xk. They cannot hit precisely here. So if they are used, say here, to define this generalized inverse, discretized generalized inverse, they still hit slightly above or below. In my case, one need to consider a non-strict inequality, but I need not pay attention, just want to describe what's happening. And now, if you have convergence in this product G1 topology, Fn belongs to D1, F belongs to D2, and it has continuous trajectories for a dual object and for the original object, then we have convergence. So the dual flow are also converging. Let's quickly recall the proof. I never actually presented it, so it's an old result. So let's assume that it's not true. Then we will have some system of starting points, a sum point S, such that this happens. So there is discontinuity in this sense. So despite Fn converging to F, these objects are not going to converge. So this is just saying that this conversion doesn't happen in the product topology. But now, since everything for the limit flow, which is typically the example in all the examples, which is exactly the case in all the examples we considered, in T, everything is continuous always. It's continuous, so we can, instead of this, just take this very specific point S. Maybe by making this discrepancy smaller. And now we will need to use the definition, what is a reversed flow, and we will consider some sequence of particles in the original flow that start before this Sn, and they, for this to be true, they need to either hit slightly above this, or they need to hit slightly below. But at the same time, they need to be used to define this trajectory. So K is this trajectory in the reverse flow. They need to approximate the trajectory of the reverse flow. They need to belong to those infinitum. They need to be used in those infinitum which require this condition, but they need to hit in such a way that the discrepancy happens. So they hit either slightly above or slightly below. Let's consider the case A. And now, because we have this uniform continuity, we can guarantee that the original, for the limit flow, this happens. So we can take some trajectories of the original flow in the way, because we know that this is infinitum, so there are some particles close to it, and we just can take another particle that's close to, at least close to that particle that delivers this infinitum. Close in the sense that it close enough, it's participant of the sequence of those particles that deliver, that is creating this infinitum. And this is by definition. This should happen because we know that they cannot hit directly, they need hit slightly above. But at the same time, we can now replace this inverse flow by this expression. Let's say at point Sn. But this convergence happen in J1, and the limit is continuous, so this is a uniform continuity, which allows us to arrive the expression in this form, where we got rid of this fixed S, and we got rid from this F. Because this convergence happens, this also becomes close to Q yod F of S, and it becomes close to this expression. And then it's just trivial to check that this should happen automatically because this yod is used to define this generalized inverse as a part of this set of trajectories that approach from above to approximate our trajectory of a dual flow. But just making recalculation, you arrive where you want it. Now, it's possible to modify these conditions a bit. For instance, starting points for this Fn can be distorted, shifted. But if these distortions happen locally uniformly, you can correct the proof. What is very important that you have continuous trajectories in your flow. And standard application is we have Harris flow, we have smooth flows, and we have convergence of smooth flows. In the sense that all finite dimensional are convergent in J1 topology as this complex, this iterative, this product, Skrochod spaces. But now we again can take some set of functions, and we can define the case particle of a new object by taking it to be the trajectory of the case particle in the original skeleton. And then this object, when taken together, are well defined because this is just a family of good measures. I forgot how to say it. And we can do this for the reverse flows too. But now that immediately gives you, by the previous theorem, that dual flows are also convergent. It's very easy to check. So for instance, we know that this is a locally finite set of points. Moreover, now we can revisit this observation about that this convergence can be discussed in terms of measures. You can define the push-forward measures are direct flows and dual flows, and you will have Vec convergence, that is Vec star convergence of these measures. So for any fixed Sk and any number of those. Obviously, you will need a possibility to integrate Gaussian densities. And as a corollary, you can now easily see why the distribution of the dual flow for the Harris flow with derivative b at phi is this. This equals to the law this. Again, you take good approximations. You know the distribution of the dual flow of those approximations, but now you know that since original flow are converging, the dual flow, the skeletons for the dual flows are also converging, which establishes the result for the whole flows. Now you can do the splitting, the fractional step method for Brownian-Webb coalescing Harris flows. Let me quickly recall. So you consider the semi-groove of ordinary differential equation. You consider a uniform mesh on the interval from 0 to t, with the size of mesh going to 0. And you define two approximations. The first one, you first apply ODE semigroup, then your Brownian web or your Harris flow. So effectively this is ODE part, this is stochastic parts, and you take this to form yn, and you take these parts to form xin. Now, if you want to do the dual, to apply this method I previously described, you need to modify this. This uses all the values on the fixed interval from 0 to t. You now need to be able to start an NES. By essentially, this works as follows. You find this tnk plus 1, where this ace belongs. You just start your splitting here. So here. And you repeat. And what happens before is ignored. You can just ignore it, effectively. So instead of doing the full iterative procedure on the whole tnk to tnk plus 1, you do it only starting from s. And because you use exactly one flow in all these constructions, you effectively build these coalescing stochastic flows on the joint probability space, the same space the original flow was defined. And then you can prove that measures are convergent. I presented a proof of this result earlier. It's actually, for some reason, it's quite longer than the result for just proper approximation of Harris flows, because you need to be careful about tails. And in particular, you can prove something for the method of empty intervals. So effectively, just take those probabilities that appear there. You also have their convergence in a proper sense. It does require some calculation, but it's very primitive. Now, so why it seems interesting to me overall? Because let us think about something like dx equals 1/2 x plus Harris noise. Coalescing Harris noise. So let us think for a moment about a stochastic partial differential equation, where this is a bad noise. Not a good noise, not a white noise, not a colored noise, but just a coalescing noise. If you try to apply splitting to this, because this part is an extremely well-behaved thing, you obtain some limit. But now, speaking of what this limit is and how to establish the existence, into which existence it should, in which terms this existence should be discussed, which is probably some martingale problem for measures. My idea was and is to try to apply the splitting combined with simultaneously considering dual flows. And maybe then you can succeed in establishing not just the existent result for the weak limit of such of the splitting procedure applied to this equation. And that's all I wanted to tell.
Okay, thank you very much. Maybe somebody have questions or comments, please.
I have a question. So you had some assumptions on non-stochastic behavior, yes, of these inverse functions.
No, I unfortunately I don't think I understand you. Do you mean this example, or do you mean what was happening before?
No, I mean you have some results when you prove the convergence of inverses.
Oh, you mean like this?
Yeah.
Yes. Effectively, here it just formulated in terms of J1 product topology. You need it to be converged, and you need to be uniformly close to origins, essentially.
Yeah. So, are there any like assumptions on the process under which you have like almost surely this convergence?
Almost surely.
Yes.
But I mean, this is effectively this is effectively a deterministic statement.
Yes, but what must be the properties of processes so that you can apply it to them?
It works for Harris flows. It works for Brownian web.
Okay.
So essentially, you need a way to just control something like this, and typically,
Yes. But the question is, are there any like properties that then you can
mm,
check them by hand so that you can apply it?
it's more about how, for me, it's more problematic to produce an example of a stochastic flow where it doesn't hold effectively.
Mhm. Okay.
Because this is just, as soon as they are bounded, or even linear coefficients with linear growth, some version of this estimate is going to hold, and this is going to be convergent, and we will enter the same situation.
Mhm. I see. Thank you.
You're
Okay,
welcome.
some other questions, please. Okay, let me ask you about the last idea of combining of heat equation and Harris noise. You definitely have to consider a measurable process related to this equation. So sometime, let me even write. Sometime one can try to get the equation with Laplacian plus noise as follows. Let us consider two different noises. One is your Harris noise, this one. Another will be like usual, just one winner process. Yeah. Then try to define the equation with this one. Yeah. And suppose that W and your noise are independent. Then when you will get the solution dy, consider the distribution of conditional distribution of y under your noise.
Mm-hmm.
Then sometime, at least for good coefficients, this conditional distribution, this is a random measure which satisfies this equation. Yeah, you see.
Yes. Yes.
So I think it can be good to just have a look. I am not insisting that it will happen, But I think that it can be productive. At least we will understand, by the way, how to apply some filtration problems to Harris
Mhm.
noise. Yeah, it is interesting
Yeah.
in its own. Yeah,
Yeah, and it's an old problem.
yeah.
Like direct approach it failed because of coefficients and the structure.
Yeah, but here you have to condition on the W
No, on
no?
noise.
On
Then
noise.
we keep noise. We keep noise.
Ah,
Yes,
yes.
and we get expectation with respect to W, and we get this generator. Yeah.
Okay, I see. Yes.
Yeah, for good noise, it works. It works. Moreover, it even works with dependent noises. We get some anticipating equations, so on, but it is different stuff.
Which is effectively a good reference as far as I understand, yeah, your works.
Yes, yeah, you can take my work about smooth and anticipating problem, and you will get a lot of reference.
I see.
Okay.
Thank you. Thank you. This is interesting.
Okay. If there are no other comments, then Georgi will say us who will be the next speaker.
Next speaker will be Andrei Pilipenko.
Okay. For today, that's all. See you next week, and bye.
Goodbye,
Bye.
everyone.
Bye bye.